I'm not saying that we have to throw out everything that we have done before, because that was very precise and it's worthy. But in terms of understanding where these gapless excitations come from, there is a simpler way. And I think it's a worthy way to deal with, to understand. Okay, so how is that? Well, we go to the original work by Griffiths, which was in '69, even before the Harris criterion, which was '73, if I remember correctly. So he was dealing with the classical Ising model. So a simple coupling constant to everyone, Ising variables, and epsilon I and j, they are just random variables, meaning that if epsilon is 0, the site is not there. If epsilon is 1, the site is there. So that's it. Epsilon I are either 0, 1 with a probability p and 1 minus p. Okay? So that's how you write down mathematically a system that is diluted. Epsilon parameterizing that. So if I draw a phase diagram of a temperature in the vertical and the probability of dilution or the dilution concentration in the horizontal axis, we get the following. When p equals 0, well, all epsilons are equal 1. So it's just the clean case, right? And in the clean Ising model in 2D, we have a transition at some critical temperature, which I'm calling TC0, TC naught. So I have a paramagnet above and a ferromagnet below. What happens when you increase P? Then you start diluting. So you expect that the temperature, the critical temperature, diminish, not lower, right? Because you are removing magnetic interactions, so you need less thermal fluctuations to destroy the magnetic crystal. So the temperature diminishes. Until some point, PC, which is called percolation threshold, where you do not have a cluster in your sample that is infinite anymore. You dilute it so much that you break your system in very tiny clusters. Doesn't need to be very tiny, but finite clusters. There is no infinite cluster anymore. There is no cluster that percolates. All right, so you cannot have a ferromagnet above PC because you don't have an infinite, you don't have the thermodynamic limit anymore. Even if your system is in the thermodynamic limit, but there is no connected cluster that is infinite anymore. So you cannot have a true ferromagnet anymore. So this is also a paramagnet. Okay, but Mr. Griffiths was very brave, and he showed that this is the distribution of Young, Lee, Fisher zeros for this problem. So I have the real temperature in the horizontal, imaginary temperature in the vertical, and there were as many zeros everywhere below TC naught. And he showed that these zeros can be arbitrarily close to the real temperature axis. How come? Does it mean that I have a non-elasticity here, non-elasticity everywhere? Something like that. I can tell you the right answer if you ask me, but since you didn't yet, I will keep going. At what? F? What's F here? Sorry, could you repeat the question? I didn't hear. P is 1/2. No, this guy here? No, this is for any P. what is 1 here? I have a TC naught. Yeah, okay, half is right here, right? Because this PC is 0.4. So if you have a half, you are in the paramagnetic side. Well, this is the transverse field, the quantum case, right? This is the ferromagnetic case. This is the classical case. I'm just changing a little bit gears here, okay? But there is an analogy of that with this, which I'm not telling you what it is yet. So if you have these sort of many zeros around, that's what we call Griffith's phase. When you have this area of zeros spread around. So the Griffith's phase is everywhere here. So I have a Griffith's paramagnet and a Griffith's ferromagnet. Everything here is Griffith's, because you have all these zeros. That's the definition. But still, there is a conventional ferromagnet in some sense, because below PC and below TC, there is infinite cluster that is the thermodynamic limit, and it is a ferromagnet because it broke Z2 symmetry. All right. So how do we understand where those zeros are coming from? Yes. Yeah, 2D. He did for 2D. For a very special reason. Okay. So the zeros, these many zeros that come here, they are due to rare regions. What is a rare region? It's a large piece of your system that is locally ferromagnet. So suppose we are here, above the percolation threshold, right? You did many dilutions, so your system is vacant, mostly. It can be very close to 1, let's say. So there is one piece here of a magnetic ion, piece there, and so on. But of course, there is a probability that all of these pieces clump together. If you are in the thermodynamic limit, this will be there. And this is a large piece. Of course, it's rare, right? That's why it's called rare region. You have to flip the coin and get many heads in a row to get all these magnetic ions together. So these are a large piece, and it is locally in the ferromagnetic side because you are below TC. So here's locally, the couplings are much stronger than KBT. So they want to be in the ferromagnetic state. Why they are not? Because they are finite, but they can be arbitrarily large. There is no rule that tells you cannot have a large piece bigger than 10,000. Nature, there is no rule, there is no law that says that I cannot flip a coin 10,000 times and get 10,000 heads. To get it happen, I have, of course, to throw out much more than 10,000 times, right? Probably exponentially to 10,000. But there will be a sequence where this will happen. And the fact that the finite of this, the probability of having these large regions is finite, so exponentially small, but still not zero, is the reason that one of these zeros come very close to the real temperature axis. So you have these many zeros. Another thing that we're going to use is that these rare regions are slow. Of course, they will fluctuate, right? You get a magnet that has, let's say, at very low temperature, and has large coupling, and its size is always composed of 10,000 ions, magnetic ions. there is very little thermal energy to make them fluctuate, but if you wait long enough, they will fluctuate. Because they cannot break Z2 symmetry. They are finite. They will fluctuate, but it will take a long time. So that's why they are slow. Okay? So these are the rare regions. So if you are in this side here, for instance, at this point of your phase diagram, a rare region looks like this. A potato, where you have all spins there, and around you have a paramagnetic bulk. A small cluster here and there, but since they are very small, they fluctuate very fast. So they are, you can consider that then as paramagnet. And they also happen in the ferromagnetic side. The ferromagnetic side, you have the bulk that is percolating, going from minus infinite to plus infinite, and it's all ferromagnet. But of course, there is a probability of having a cavity there, a hole that is paramagnetic because most things here are diluted. But inside this cavity, which is big, is a big cavity, there is also a potato there, a large region that is locally ferromagnetic. And this large region here has nothing to do with the bulk. They are not connected. So you have both these rare regions in both sides of your phase boundary. All right. Any questions so far? Yeah, you can have some yeah, this is a disorder region. It's a paramagnetic region, paramagnetic cavity. I just thought that diluting everything will convince everyone more easily. But you could have some things connecting them, but very weakly, and they connect these spaces larger than the associated correlation length, so they're practically independent. That's what I need. All right. Yes, yes. I need them to be slow. And will be, this is a essential point that I will tell you right away. As was inquired before, we were, last class, we were talking about this model. Transverse fluidizing model, Gi, sigma I. I can put not in one dimension, but in any dimension, Ij. I will even assume a uniform field, external field that experimentalists can put there. And I can think of something like this. I have a probability of J are distributed according to some distribution, let's say something like this. And I can put a field that's right here. This is the value of H. So we know that H is greater than the great majority of J's. So we are in the paramagnetic side. But nonetheless, there are some couplings that are bigger than the fields. So I can have a piece of my system that all the couplings here are bigger than the local fields. Right? So this is a rare region in that model. Okay, so far, who cares, right? They are rare. So who cares about rare things? Usually when we think of disorder in the conventional old ways, we thought, okay, we can average over disorder. These are atypical configurations of disorder. They barely appear. The probability of this configuration is exponentially rare. It doesn't have nothing to do with the average. But I will tell you that all that physics are due to these rare regions. And therefore, conventional methods fail to grasp these Griffith's singularities. So that's the title of the class, The Greatness of Rare Regions, or Griffith Singularity Reload, because we already saw Griffith Singularities last class. So again, I will use this order as at our favor and simplify the model. So I will do the simplification. Rare regions are dilute. There is one rare region here. Probably the other rare region is crossing the street. They are dilute because they are rare. If they are dilute, they do not talk to each other, right? So they are independent. Why they are independent? Because they are far apart, many times than the correlation length of the bulk. So if I do something here in the bulk, this information will be spread up to the correlation length, and the next rare region is much farther away. If I flip this rare region here, the other rare region does not care. So rare regions are independent. Okay, this will help us to compute their effects. For instance, if you want the magnetization coming from the rare regions, you put an external field, and you're going to polarize the rare regions somehow. So I know if I put an external field here, I know the magnetization coming from this rare region, I know the magnetization coming from the other rare region, and then I just sum of them. Because they do not interact, so their effects, the combined effects, is just a superposition. Right? So since I want to tell about other things that we discussed, that you voted last class, I'll just compute one thing about rare regions. Okay? And I will compute the density of states, because I want to understand why the gap is 0. So how to compute the rare regions effects? That's the prescription. We need 2 ingredients. Which is the rare region probability of appearance. How do I write appearance? Something like that. And the rare region contribution to the observable. With that, we can understand everything that I presented the last class about Griffith singularities. Let's go. This ingredient A is very easy, right? What's the probability of appearance of a rare region? We know, it's exponentially rare. And this guy here is what I'm going to do. It depends on the observable. So I think maybe the easiest observable is the density of states. So I want to compute so I'm in the paramagnetic side. And suppose I'm here more or less. And I ask you, what is the density of state of the clean system? There is a gap, so density of states, rho omega of omega. What's the density of states? The number of states in the Hamiltonian, eigenstates of the Hamiltonian that has energy omega above the ground state, right? So because there is a gap, and this is the bulk gap, there is no states between 0 and that gap, right? Otherwise, it wouldn't be a gap, and then there is some density states. I don't know, it can be something different from this curve, but let's assume it's like this. There is a gap, right? So it's hard to excite this paramagnet. If you want to give him small energy, it doesn't accept. If you want to polarize it, you have to pay the gap. The associated magnetic energy that your field has to give has to be bigger than the gap. Otherwise, it does not polarize. Susceptibility will be very small, things like that. So now let's suppose that we put this order, add this order to the problem. Now we have the rare regions. So how the rare regions will change these density of states? Well, we have now to do gradient B. So we have this Hamiltonian. So locally, all the couplings here are bigger than the field. So essentially, this is a single degree of freedom that can be either everybody up or everybody down. Let's say that I switch off the transverse field. What are the states? A region spectrum or local spectrum. So if H is 0, I have everybody up, and I have everybody down as the ground states, right? Now I flip one of the spins in the rare region, and I have a bunch of states up here. But of course, this is of order J. 2J to be precisely. But, well, maybe there is a dangling bond up here that only is connected to 1J, so it's 1J. It's of order J. But now I switch on the field, right? So, which is the real situation? Remember that the local Hamiltonian is minus J, sum of sigma I, sigma J, Z and Z, minus H, sum of sigma I X. And these J's are much big, or all bigger, or mostly bigger than the H's. So this is like minus J, and I have an effective degree of freedom that is representing all these spins. And of course, I have an effective field that is trying to make this coherent superparamagnet oscillate. So when I switch off H, I have all these states up there, but what happened to those states here? Well, the degeneracy is lifted, right? So I have the ups and the downs. There is a lifting of delta of rare region. That's the energy that you have to pay to excite this rare region here. Suppose the rare region is the ground state. What's the minimal energy that you have to give to the rare region so it excites? Is this RR here. So this delta RR is the state that will fill up our, so this is delta RR. I put a state now in the middle of the gap. How many states I have to put there? Well, it's exponentially small states, right? Because, so who cares? I'll show you that it's important. Let's compute this delta RR. How is that? Well, again, we use that assumption that it's locally in the ferromagnetic phase, so all J's are bigger than all fields. And I can do perturbation theory here. So in first order of perturbation theory, what you have to do? You have to, that's your perturbation. And that's your H naught. So I put the perturbation in this state. What does it do? It gets this state and flip one spin only. Does it connect with this other one here? No, it does not. So in first order, nothing happens. If you go to second order, then you have to multiply to get the 2 square. So I will get sigma 1x and sigma 2x. So I flip 2 spins. Does it connect with this guy? Not yet. So I have to go to third order. I flip 3 spins. Does it connect? Not yet. So which order of perturbation theory gives me a finite correction? In nth order of perturbation theory. So this delta, RR, will be what? Well, each order perturbation theory gives you an H. For instance, in first order perturbation theory, just H, right? In second order, I get H squared divided by the gap, J, and so on. So the third, in nth order, I'll get E over J to the power n minus 1. And the H is smaller than the J. So for any much bigger than 1, n minus 1 is just n. This is H exponential of minus n. We divide by some number that I will call A. And we can see what's A. It's log of J over H. All right, but n is the number of spins in the rare region. So it's the volume of the rare region. So I will just put here V of rare region, and I will put here the volume of the rare region. That's what we would expect, right? If it's locally in the order state. You have two states that are exponentially close to each other in the volume of the rare region of the system. All right? Now you are all set. Because what is the contribution of the rare region coming from, the contribution to the density of states coming from this rare region? Contribution to the density of states is delta omega minus delta gap of the rare region. Now I have to sum up everything. So rho of rare regions, I will sum over all rare regions the contribution of the rare region weighted by the probability of having that rare region, ingredient A. That's the sum that we have to do. How much is this probability? As we've seen, I have to flip the coin many times to find the rare region, which I just erased. So this is exponentially small in the volume of the rare region. And I need a constant here that I will call B just to have a bidimensionality, right? So this has to do with the microscopics of these random variables. How likely I can find a rare region there? It will depend on this P, right? And this we know. This is exponentially small. Now we can do the integration, because there is a delta there, right? So that's why I choose these observable, because it's very easy to compute. You just need to do a delta integration. So how is that? Remember, whenever there is a function inside the delta, the Dirac delta, I need to divide 1 over the modulus of the derivative of the function. But the derivative of the function is itself, because it's exponential. But the exponential is equal to omega, so I get 1 over omega here. But now I need to put the optimal value of the rare region here, right? So exponential, oh, there is exponential. This is 1 over omega, that would be something like this, right? Wow, that would say, great. The rare regions are putting lots of state at low frequency, so there is no gap. But then comes this exponential here that, but let's keep doing. So how much is minus VRR? Because I have minus VRR here. So minus VRR, if I take the log, it's A log omega, right? Because I take the log, the things goes away. So I get minus VRR, I get A log omega divided by B. Okay, so I have A divided by B log omega. And now I put this guy there, so this is 1 minus A over B. Oh, so I didn't kill the power law. It's still there. So when A divided by B is less than 1, I get a divergence. I get this. So this is rho rare region. So all the low energy physics is coming from the rare regions, because they fill up the gap when that happens. And I can assure you that there is a better way to do these calculations, and whenever you get close to the critical point, this number A over B becomes less than 1. Just because B becomes too big, because close the critical point, the rare regions, they become less and less rare, so B increases. Yeah, zero temperature, I'm here. Yeah, somewhere inside the Griffiths paramagnet. Where this point start? This point start when H hits the maximum of J. If the H is right here, I'm in the conventional paramagnet. Because there is no rare region, and I diminish J, H until I reach here. And this is the start of the Griffiths paramagnetic region. When I reach the critical point, then the rare regions talk to each other. Because now the bulk is not, the correlation length of the bulk is not small anymore. And you cannot use the independent assumption anymore. Then you have to do the SDRG that we did yesterday. All right. Yes, yes. And that's the answer. That's the exact answer if you do that via SDRG. And you get this A over B is SDRG result. A over B is equal 1 over Z. So when you go to the critical point, remember Z is infinite. And this goes to 0, you get a huge divergent density of state, meaning that the rare regions are really doing everything in this problem. And since they are rare, they are not in the middle of the Gaussian, they are in the tail of the Gaussian. Conventional averaging disorder methods will not capture them. Although they are rare, they are very slow. How can you think of that? One way is that if you put a small energy to the system, there is a gap. So the book doesn't care, but they accept. So all the dynamics, everything is happening in the rare regions. If you apply a tiny magnetic field, the book does not care, because you have to pay energy H to align the paramagnetic spin. But if you are in this rare region, you have to pay only this exponentially small energy to align the rare region. And they stay aligned in the field. So the magnetic response is all due to the rare regions. So all these singularities that we wrote yesterday in the Griffiths in the Griffiths phase are due to those rare regions. How do we see that in the SDRG? Remember, if I have something like this, I decimate lots of J until I hit here. So when I decimate all of these J's, I clump them together, and I have the rare regions. From here down, I just decimate fields. So I get a huge bulk that's paramagnet. So the SDRG, it builds up the rare regions. But probably it's hard to see from first glance from the lectures of yesterday. All right, that's what I had to tell you about Griffiths. Actually, that's not true, because now I will switch gears. True. Why is it here? That doesn't matter. Now I switch gears, and I will introduce dissipation to this problem. This is a model, a magnetic model for localized spins that are not talking to anything else, right? But if you are in a metal, for instance, there are electrons scattering around here, and these electrons will interact with the local spins, and they will exchange some energy, and things will happen, right? So I want now to introduce a new model of this magnetic system in as an open system. So I will couple this transverse field easing model to a set of harmonic oscillators. And they will act as a bath, where magnetic energy can come out of here and go to the bath. So there will be, whenever a spin flip here, something happen with those harmonic oscillators, and see what changes. So the model that I will consider is this one here. So the first two terms, let's see if I can do as Vitor. Yeah, just work with Vitor, doesn't work with me. Yeah, Vitor, you have the hand, I don't. So the first two terms are the easing transverse field chain, And this is our set of harmonic oscillators, A DAG and A bosonic operators. And these are the frequencies of the harmonic oscillators. So I put a set of harmonic oscillators to each spin. It's just a model. And I will couple, as Vitor did, right? It was in his last lecture, this A DAG plus A is the minimal, called minimal coupling. With not the light or his floquet, whatever, but spins of our magnetic system. So I have here is interaction, here are the fluctuations, and here's the dissipation. It's just a model, right? We could come up with other models, just let's bear with this one here. Because this one here, this dissipation does something that I think very interesting, which is the following. Whenever I flip the spin, remember, this is p squared plus x squared, right? This is the harmonic oscillator in second quantization. And this term here, A DAG plus A, is what? This is x, meaning that you couple the spins to the position of the oscillators. So this is x squared, and this is x. So I can complete squares. So the minimum of the oscillators will depend on the sign or direction of the spin. So if it spins up, the oscillators are to the left. If it spins down, the oscillators are to the right. Whatever, you have to complete square, right? But this minimum that you find will depend on this number, which is plus minus 1. And therefore, if these quantum fluctuations flip one spin, you have to drag all the oscillators together. And if the quantum fluctuation flips back, you have to grab all the oscillators together again, back. And these provide us dissipation to the quantum fluctuations, meaning that you are going to the classical world. You are killing the quantum fluctuations somehow. That's the expectation of this model. And this model was cooked up by Caldeira and Leggett a long time ago, and I'm just putting in the context of, what is this? In the context of Ising model. All right. So why it's not going? Yeah, probably I did something that I shouldn't. Yeah, if you, okay. So what is the result? Let's not talk about how you solve it. Let's just think of how we understand this problem in the context of rare regions, right? So what was going on here? I have a rare region that is everybody up, right? And each of these, oh, it's not going. Por que não aparece aqui? Yeah, it's frozen. So we are passing through technicalities. We appreciate your patience. So each of these spins is coupled to, yes, now it's working, thanks. Each of these spins coupled to a set of harmonic oscillators. So they want to tunnel from everybody up to everybody down. So if you were only one spin, it tunnels and it grabs a set of harmonic oscillators. It can do that. This coupling that we are putting there, this lambda, I will assume that is very, very tiny, very, very small. So it doesn't do much, right? This energy scale is much smaller than the other energy scales. But in the rare region, it just tunnels coherently between everybody up and everybody down. So it doesn't have to grab just one set of harmonic oscillators. It has to grab the volume are harmonic oscillators. And then that energy scale will sum up with the size of the rare region. So this energy scale increase with the rare region. So if the rare region is very big, what you gonna think gonna happen? This is gonna dominate everything. And the Caldeira and Leggett taught us that there is a threshold. When this VRR is very big, it stops tunneling. Because it's so many oscillators that you have to drag that you cannot. They will anchor you. The rare region will be anchored here in one of these states. But how come a rare region become in one of the states? It means that it broke this symmetry. But how it broke? It underwent a phase transition. This is called dissipative phase transition. So it locally acquires magnetization, regardless the bulk. The bulk still has its gap, doing whatever it wants to do. It doesn't care about the rare region. But the rare region undergoes its own phase transition regardless of the bulk. And this is a finite rare region. So where is the infinite? The infinite is on the oscillators. Because there is it's an open quantum system. It's not a single one, a closed one anymore. So because the rare region underwent its magnetic transition regardless of the bulk, the magnetization that will appear, remember the magnetization, if I draw the magnetization do something like this, right? In the clean case and in the dirty case, as we saw yesterday. But now, this is the dissipationless. Now, the dissipative one will not do this. What will you do? Coming from here, because here I start to having the rare regions. So the rare region will do something like this. So this is the dissipative. So the magnetization starts here. And because it's not a singularity in the bulk, we call it smeared. It's a smeared transition. It's not at a sharp point of your... It happens here, but it's not due to a bulk singularity. We really put this zero to the real axis. Yes? Only the big ones, right? Mm-hmm. The tiny ones can still grab one or two or three set of oscillators. They'll still be fluctuating. Not all of them. And then I keep diminishing the transverse field. The transverse field, I do this. These rare regions become bigger or more robust. They grab more oscillators. And then they start frozen together. And that's why it keeps increasing. And this increase here is exponentially small. This is a power law, right? We saw that for the dissipationless, we get M is proportional to minus delta to beta, the parameter beta. Here in the dissipative case, because the rare region is exponentially small, you get an exponentially small magnetization. So the magnetization will be something exponential of minus 1 over delta, something like that. Something that when delta, well, now delta is not this delta. This let's call this tiny delta from the onset of the Griffiths paramagnet. So this is tiny delta here. So when delta goes to 0, this goes to infinite, minus infinite, so it's exponentially small magnetization. Yes? Yes, yes.
In order to have some hope of measuring that effect, you have to apply a very small magnetic field to break the symmetry.
No, they will respond. Yeah, the question is the following. I have one rare region there and another rare region there. They do not talk to each other, right? That's what we have we have said here, right? But in this case, I have this rare region up here, and and the other rare region right there. And suppose they are above the critical size, so they freeze. So because one freeze, and the correlation length is finite, but even though it's finite, it talks exponentially weak to the other one, because the effective interaction between them is exponential of their distance, let's say L, divided by the correlation length. But this exponential weak interaction is enough then to talk and say, I went up, and so the other one goes up. So they coherently go together. Well, who is mediating the interaction? Then you have to tell. In this case, I'm saying that's the paramagnetic bulk. Paramagnetic bulk is mediating this interaction. Very good questions, and not and subtle ones, actually. So this is what I just tell. You have the rare regions. J is typically greater than H. You have the paramagnet, whatever. These can be our distributions of couplings and fields. This is characterizing the spectral function of the oscillators. This is an important point, but I will not go into details. I'm considering ohmic dissipation, which is important. So the spectral function is the number of states available to exchange energy. You can think of more or less like that. So the number of states increase linearly with energy. And there is this parameter alpha, which I will say it's very small because lambda is very small. And it's proportional to lambda. So the cartoon is the cartoon that we had before, but they are tunneling in the dissipative environment. It's a viscous environment. So how do you do that? How do what we expect is just what I said, that now you have these rare regions, right? If they are strongly coupled, they can act as a single one and so on. So you have these rare regions, and the magnetization will be something like that. Big rare regions are frozen. Small rare regions, they still fluctuate, so no magnetization here, and so on. So that's what I just drew there. And there is a randomization group to show how is this. I will not go into the detail, but probably you have to solve this set of couple equations. And it looks like horrible, but it's not, because there is no critical point. So how do you solve that? You assume there is a critical point, and you arrive in a contradiction. And the contradiction is because of the size of the rare region, critical size of a region, it freezes. So this is a transition that has no critical point. It's a continuous transition without a critical point. That's what we call a smeared transition. Just what I said, right? Without smearing and without dissipation, with dissipation. So more or less, you do that SCDRG that I told you before, and the big rare regions, they become frozen, while the small rare regions, they still tunnel. Yeah, that's it. Any questions from smeared phase transitions? Of course, that was very fast, and but just to give you the flavor of the mechanism behind it. You need to couple it to some dissipative bath, so you can somehow prevent quantum fluctuations. Because, yeah. Well, it's there, right? But you like my drawing, right? Yeah, WD is weakly disordered. So it's the Griffiths paramagnet, the strongly disordered, the conventional paramagnet in this case. I'm showing this in this context of transverse field easy mod, but it applies to many other phase transitions. Yes, that's what I said. What Griffiths showed that these zeros in the dissipationless case, they are arbitrarily close to the real axis. Now we touch. Now because we did have the infinite in the, because of the oscillators is an infinite set, then you have the thermodynamic limit. Then this guy really touch.
So for the Griffiths regions there, before this, they don't touch.
They do not. But they are,
Critical point they do.
at the critical point they do.
Okay, just like any regular transition.
Yes, yes. They do not touch, but they are arbitrarily close to. So that's why you have those singularities of yesterday. They do not touch, but to all practical purposes, I will not say they do, but they are there.
So that's how it can be gapless but not critical.
That's correct. Yeah, there's no divergence. The correlation length is the size of the region, yes. Sorry, could you repeat the question? Mm. Mm-hmm. Yes. No, I need an infinite set of modes. If you have a finite set, then again you come back to that these zeros are not exactly touching, but even be more arbitrarily close. But you need the infinite to really touch the real axis. No, it doesn't matter. Doesn't matter. I just assume that they are very small, so they are not messing things up too much. I'm connecting perturbatively with the. If they are too strong, then each spin talks to the bath and comes back to monogamy, as Fernando was saying one of the previous lectures. Yes. Yes, that's very hard, right? Because everything that exponentially small will be hard. So it's hard to see in numerical simulations. The best thing that you have is this concavity that goes up here. That's you can see in numerics, and that has been seen. But the very small, of course, is hard. You come up to something like here. We have some convincing numerics for that. Yes? Yes, the geometry, it plays a role, even here, right? When I put these things goes to, there is, if you want the equality, there is a constant that depends on the geometry of the rare region. So each rare region have its own constant here. But to do that calculation, I don't need that constant, because what matters is what is the exponential. So yes, this constant will change non-universal quantities, like where is this point, if it's a little bit left or right, or actually the constant that comes in front of here, but not the functional form. Thanks. Any more questions? So, okay, as was a tight yesterday, so I talk about smearing, and now talk about dynamics, right? How do I change? Okay, it's disappearing. Where is that? What is the... Okay, I have to do this one here. Okay, now I got it. So this was mirroring, this is the dynamics. Why is not coming up? Come on. Where is everything? Agora eu quero esse aqui. É. Vai no PDF, não está abrindo? Não, não é nesse não. Não. É esse aqui. All right. So much for dynamics now. Thanks, Fernando and Vitor for talking about a lot of dynamics, so we can go a little bit fast, right? So what I'm interested is on the dynamics of closed quantum system. Mirroring is open, but now let's come back to closed. So I will prepare a state, a system in a state, psi 0. I will do some quench, Sundam quench, and let it evolve unitarily, okay? And then I will ask, what's the probability to come back to the original state? That's called a Low-Schmidt amplitude or Low-Schmidt echo. So if I say that IT is beta, what's that? Looks like a partition function, exponential beta h. But I'm not doing the trace. I'm doing just average value on the ground state. So it's some sort of partition function. Nonetheless, it is a function. And if it is a function, it obeys the Weierstrass factorization theorem. And as before, we have zeros, right? In the complex plane. Now, the complex plane is in time. I have real time and imaginary time. So the zeros will appear in the imaginary part. And maybe when they touch, if they touch the real-time axis, something interesting can happen, some non-analyticity in this function f here, which is the log of z, right? If I call this f as analogous of free energy, so it's a dynamical free energy, I would have a non-analyticity in this dynamical free energy coming from the zeros of this dynamical partition function, Low-Schmidt echo. All right, so far sounds like a curiosity, right? But you're doing dynamics nonetheless. Later I will try to make connections with some observables. But so far, we are back to the first class Yang-Lee-Fisher zeros, right? So what is the system? Well, is the transverse field Ising chain, as we are just playing with, but let's bear with the clean one, for instance. We know that when H is greater than J, we are in the paramagnetic state. Below it, or otherwise, we are in the ferromagnetic state where there is a spontaneous symmetry breaking in the thermodynamic limit. And the spectral gap goes to 0 at the quantum critical point only, and the magnetization goes to 0 there as well, and is 0 in the paramagnetic side. Okay. So the non-equilibrium protocol is the following. We start with some H0, and I will start H0 infinite, for instance. So all the spins are aligned to the field. And then I quench H0 to some finite value. It can be either bigger or smaller than J. This problem can be solved in 1D exactly, and in the clean case, even analytically. As Fernando was telling us today, there is a fermionization technique. You can make these spins into fermionic variables. And this fermion model, you have hopping terms, you have on-site energy, and you have superconducting terms. As will appear C, C, and C daga, C daga. But we don't need the fancy Majorana fermions here. So after some small calculations, like 10 to 15 pages, you can compute this Loschmidt amplitude. And that's the result. So what appears in this result? Well, this appears this function here, which is a function that have the memory of where you came from and where you went to. And there is this omega here, which is simply the spectrum of the quasi-fermions, the quasi-particles, in the fermionic language. We can set this function to 0 as a productory, which is good because now I just set each of these terms to 0 and I get the zeros, right? Like the Weierstrass function here, the theorem. So these are the zeros. That's it. So we don't need to bear with these functions. I suppose it's more intuitive if I draw them to you. So that's it. If you come back here, the real part has this m, where m is an integer. So you have a lot of zeros that repeat with some period in time. And this period has to do with the spectrum of the system. The imaginary part does not repeat. So you have copies, like this set of zeros are copy. This is a copy of that one, and so on, and so on. So these are the Fisher or Lee-Yang-Fisher zeros for a quench of, I don't know, maybe 100, let's size. 100 spins, and those are the zeros that I drew here. And I call these, there is a copy of the other one, I forgot how it's one leaf, another leaf, and so on. So this is a quench from infinite to H, and H is 1/3 of the J. So meaning that I cross the transition. I start from here, infinite, and I cross to 1/3. So you can see that these zeros are crossing the real-time axis. They are not touching, but remember, they are very close. If I increase the number, the size of the lattice, there will be more dense, and the dashed line is the infinite limit, the infinite size limit, thermodynamic limit. So if I compute this dynamical free energy, it has kinks. There's a kink here, so when H was 0, and when H was 1/3, what are those here? I have a singularity appears at 2 point something, so 2 point something is this one here, and 6 whatever, 7 more or less, and so on. But if I do a quench that do not cross the transition, like this H is a little bit higher than J, all the zeros are up here. So none of them are touching the, or pinching the, or crossing the real time. So I have functions that are smooth and analytic, nothing happens. So why is this interesting? The non-elasticity in time, which is certainly out of equilibrium, is developing only when I'm crossing the equilibrium phase transition, in this case, quantum phase transition. So the dynamics know if you cross or not quantum phase transition. So this is interesting. For this model, you can show that there is one-to-one correspondence. These non-elasticities, the zeros only cross the real-time axis when you cross the equilibrium quantum phase transition. Later, people realized that tried these things to many other models, and the correspondence is not one-to-one. There are some cases when you cross the equilibrium phase transition, but nothing appears in the dynamics, and also the other way around. So this became a field of its own to understand where those singularities are coming from and so on. But in this case, we understand that the rare regions, the non-elasticities are tied to the non-elasticity of the equilibrium case. So disorder, of course. Again, we know this, what's written here in the equilibrium case. If all fields are bigger than all J's, we are in the conventional paramagnetic side. Otherwise, and there is a gap, the spectral gap is finite, and in red we have the magnetization is 0. In the other way around, in the ferromagnetic side, with a finite magnetization and a finite gap. In the middle, we have the rare regions, right? These are rare region, exponentially rare, so it takes an exponentially large time to fluctuate from up and down, and so on. And this gapless, right? Now you're in the Griffiths paramagnetic side. So I pose the question, do these low rare regions, do they put some zeros of Yang-Lee Fisher near the real-time axis, like the equilibrium Griffiths did for the equilibrium case? That's the question that we addressed. Well, this is the calculation that we did in the blackboard, right? So for the equilibrium, I just could have shown that. All right. So how do we analyze the dynamics? Maybe I could come up with some sort of RG, dynamical RG, but I want to, firstly, to draw precise statements. And because we can fermionize this problem, we can diagonalize it for really big systems and do exact diagonalization so I can give exact results. So that's what we did. That's what I'm going to show you here, the numerical results. So sorry for numerics, but we can make sense of these numerics the same way we make sense of these rare regions here. So what I'm going to do, I'm going to analyze a single defect, a single rare region. I will not draw a random distribution where J's are all distributed and a complicated distribution. No. Let's just think of a single rare region in a uniform homogeneous bulk. So I have the rare region here, and everywhere else I have the bulk, okay? And I'm doing that quench from H infinite to some finite H. And I will make this finite energy between the coupling of the bulk and the coupling of the rare region, meaning that I'm doing a quantum quench. Maybe I have a picture here. I'm doing a quantum quench. Where is this quantum quench? It's not here. I'm doing a quantum quench from deep in the conventional paramagnet, H infinite, to the Griffiths paramagnet. So I'm not crossing the bulk transition. In the clean case, I would have analytic, everything analytic, right? The zeros are up in the sky. They are not near the real-time axis. So what's the result? The result is the following. So let's say a rare region of size 1 and equal to JB. Of course, the zeros are up here, as we have seen. And I'm drawing just one here. Remember, there are the copies around there, but they are not showing this graph. And this is the dynamical free energy. Well, everything analytic. So I'm increasing the value of J. So I increase it 2 times. It's not still a rare region because it's still small, right? But I'm increasing. But nothing happens. So I have a migrating 0. So now J R is equal H. So I'm on the onset of entering the Griffiths paramagnet. And well, nothing much happened. So on, so I'm increasing that a lot, and nothing's happening. Well, of course nothing happens. That's not a rare region, right? This is just a link. The rare region, I told you, rare region is here, large piece of the system. So let's increase the rare region. So twice, oh, now I have two migrating zeros. And 3 times, 4, size 4. Now I have somewhat large region, 15 spins, and I have a set of zeros here that migrate. And what happens to the free energy? Now I'm developing a kink. Okay. But I did not cross the bulk transition. So what the conclusion that we have is the following. I will do this interpretation. The bulk and the rare regions dynamics are decoupled. I can understand this result as the following. Cut the rare region out of the bulk and do the dynamics of the rare region independent of the dynamics of the bulk. That's my claim. And this, of course, simplifies the problem. As we just did here, right? I will just compute the rare region's contribution regardless of the bulk. The bulk is doing whatever he wants, and the rare regions also. So to show that, I did the following. It's the same plot as before. But now, in cross is the dynamics of a rare region. I cut the bulk, I get that 15 size chain, and did the quench of that open chain. It's not anymore periodic. It's that piece of the system of 15 lattice size. And these are the zeros, the cross. They match what we had before. And these are the zeros of the bulk. So I cut the system, and these are the zeros of the bulk. They do not match exactly. But you know what? I don't care. Because they are up there, they do not respond for any non-analyticity. Whatever contribution this bulk gives is analytic, as we did here. This is an analytic contribution here. The non-analyticities are due to the rare region. All right. So that's so much for a single rare region. Now let's do 2 rare regions. Do they talk to each other? This is not a simple question to answer because this is a high energetic dynamics. Doesn't mean that one rare region is very far from each other. They talk through the correlation length of the bulk. The correlation length is an equilibrium concept. This is out of equilibrium. I don't know what's going on. So let's see what happens when I have 2 rare regions. One here, rare region 1, and another there, rare region 2. So these are the zeros that I get. I get 2 sets of 0, not 1 set of 0. And I get, what is this? The black curve, which is below the red dashed one. You can see there is a black curve there, right? So look what I have. I have a peak here, another peak there, another here, another there. Well, things are becoming messy, not like, not so much as before that we have these regular peaks. So let's try to understand that. The first thing I'm doing is the following. I'm computing just the case of a single rare region. So I have a rare region and a bulk. And I get the orange curve. Now I do the same. I raise the second rare region, the first rare region. I have only the second rare region. I have the green curve. And then I sum the green plus the orange. These are the red dashed, which match when I have both rare regions. So all these singularities is just a sum of the singularities. Like we had here, we have a zero of one rare region and a zero of the other rare regions, So they just add up. It's a superposition. So it's working. So yeah, that's more of the same. To give you a flavor, you can say, why do I care about low-Schmitt echo? I care about observables like magnetization or something else. So let's take a different approach now. I will compute the following. I will compute the energy difference from the ground state. So I'm removing the ground state, and this EI, here is the local Hamiltonian. So I have the local field, half coupling to the left, half coupling to the right. So the Hamiltonian is the sum of these AIs, operators. And I'm taking the average value of this AI operator in the ground state of the system, and this is the evolved state of the system. So I'm just measuring the energy above the ground state. Because we are doing dynamics. You remove it from the ground state, excited, and you are seeing the density energy throughout the chain. All right? So you have time in the horizontal, and in the bottom, in the vertical, we have this quantity delta EI, which is here. So blue means that you are locally not excited, and red means that you are highly excited. So I have two rare regions. One rare region is from site 0 to site 20. So this is 20 sites length rare region. And the second rare region is 5 site lengths, and this is here. So I do the quench and compute this observable here, the density of energy. So the bulk, what's going on to the bulk? The bulk is, nothing is happening in the bulk. It is the ground state. Why? Because you are doing a quench that goes from the paramagnet to the paramagnet. So you barely excite the bulk. Because you are in the paramagnet, you're still the paramagnet, so the ground states are more or less like the same. You barely excite it. Actually, it doesn't look there is any excitation at all. Of course there is, but very, very tiny ones. But what's going on to the rare region? Well, remember, the rare region, you cross its local transition. Because now the rare region is in the ferromagnetic phase when you do the quench. And before it was in the paramagnet. So how do you express the original state, which is a paramagnet, in a ferromagnetic state? Of course, there are tons of excitations. And that's the excitations here. That's why it's highly excited. You can see even the light cones appear here. That there's excitations that are going up and down with the local speed of light here. And these excitations do not decay to the bulk. So they are confined there. You can do the same game for the energy current. Because energy is a conserved quantity, you can compute the energy current, and the energy current is this observable here. So the energy current, Well, if it's green, there is no energy current, so the bulk, nothing's in the bulk, and you see better now the light cones there. So everything is confined to the rare regions, yes. Yes, that's the question that I was going to go there. So before I answer your question, let me just wrap up here. So each rare region has its own set of Fisher zeros, Young-Lee Fisher zeros. So when you have many rare regions that they are different, you have many zeros that are arbitrarily close to the real-time axis. So you're going to have some region in some time window where those zeros are. And following Griffiths, I call this dynamical Griffiths phase or time Griffiths phase, you name it. Yeah, so I think I can stop here and take questions. So there was already one question, and he said, well, if you break integrability, what's going to happen? You excite the system. If it's not integrable, you expect, as we learned from Boltzmann, to thermalize. So these excitations should decay to the bulk, and you have a thermal, a state in thermal equilibrium. And this takes time, of course. If it's many-body localized or not, let's not go to there. I expect that it will thermalize at some point eventually. But while it does not thermalize, we can see this physics. Why you can see this physics? Because this is fast energy physics. These things going up and down here is going to the speed of light. This is fast dynamics. So contrarily to what had in the equilibrium case, where the rare region is slow, they're slowly tunneling, these rare regions are exciting and fast. So these dynamics can be probed before thermalization. Does it, then you can argue, when you break integrability, these will decay very fast to the bulk, and you'll not be able to see it. I can argue the following. The bulk is gapped, so it does not accept any excitation. So there will be excitations here that they will say, bulk, do you accept me? If you do not match, if you are here in the bulk, they will not accept. So they will be touching, trying to tunnel many times, even before something happens, when two excitations come and something else happens. And then we will thermalize. But that's my argument to say that it's going to take time to these excitations go into the bulk. Another argument is the following. This is locally ferromagnetic, while this is locally paramagnetic. They are in different phases. So if this is large enough, you can say that the quantum numbers that these excitations carry, which are conserved because it's a new phase of matter locally there, they do not match with the quantum numbers in the paramagnetic side. So maybe they will not easily decay to the bulk. So this will take time anyways, even if it's not integrable. And these physics should survive at least some long time. But of course, I'm very eager to see that in other numerics for non-integrable systems. But of course, you can imagine that's hard, right? Especially because you need large systems, you need a large rare region and things like this. Well, I would be happy if I read 60. From 0 to 60, one rare region of 20, I would be very happy. Yeah, for the MRG, right? Well, I don't know. DMRG can do short times, and I think this could be doable to DMRG up to, I don't know, 10 or something. Yeah. Oh, no, exact normalization, yeah, then yeah. 20 sites is already, yes. Maybe it's for 20, right? I suppose full dynamics is, the maximum is 16. Full dynamics, 16. Um, because we need the full dynamics, and not 20 is, I think, is already large. But okay, 16, make a region of size 5 or so. It would be like those experiments that Fernando was showing about this many bar localization in cold atoms. Lots of, yeah, should be, yeah. That's a project, open project, yeah. I had a DMRG postdoc, but he decided to earn money and quit academia, so I need another DMRG guy now. Yeah, we can talk. All right. Any further questions? Yes. Yeah, yeah. You don't want to ever over disorder here, right? You want to see the confinement of excitations in the rare regions. So no disorder average here. On everything, you wash out everything. These rare regions, they are easy to understand in the concept of strong correlated system, right? Because as I put here, it's a large piece of system locally in one of the phase. So I'm looking at states of matter where disorder does not mess up with the phase of the phase diagram. Under some localization, there is no clean counterpart to the insulator. So I do not have a rare region. So this is the kind of effects of disorder that it stabilizes a new phase of matter, which is in case Anderson insulator. So I don't have a rare region in this case. Of course, you can say that inside Anderson insulator, there is a metallic piece there, like a rare region. Then you can cook up things like that. But the concept I'm saying here, I'm just looking at two phases, and disorder didn't mess up with this phase. But okay, you can somehow adapt these concepts to this case, but that's not had been done. Further questions? Well, if not, I think we end this nice school here, or mini course if you want. For me, it's like more like a school than a mini course. It was a great pleasure to have you all here. Thanks for coming. Thanks a lot to Joey and to Rui for helping with the organization. Thanks a lot to Vitor and Fernando for accepting our invitation and coming and delivering high-level lectures. I hope that you all have a good time scientifically and personally, meeting each other and in your conversation in the poster sessions. Later, probably with a high probability, you receive a message from the organization where you have to fill a form responding or answering questions like, what did you think of... oh, it's already there. So, well, it's probability 1 now. Please answer this form very carefully and thoughtfully. because this is a feedback that help us to improve and do a better job next time. Say whatever you think is important. Oh, the commuting from metro is hard, the hotel is not good, or it's good, or the lectures are very good, then you send directly to me. The lectures are bad, the lectures sent to Rui. That's what I have to say. I also want to make it registered that we thank the staff, the TI guys, and our secretaries, Elisa and Humberto. They help a lot, and certainly they do the heavy weightlifting. And I think that's it. So I wish many success to the career of your younglings, the young ones, and see you in the next, hopefully, the near future. Thanks.